Welcome back to the second half of general chemistry. We'll take a look at the syllabus for a second. All this beginning stuff is good information, but it's not particularly relevant to the course, which is 214. Principles of Chemistry, second semester. Okay, so we're going to scroll through these. You already know that the syllabus is made up of 3 parts. And the second part is the most important because that's where I get to tell you what we're going to do. Don't ask me how to tell if the school is going to be open on a snow day, because I tried the snow line and it didn't work. So I guess maybe the local radio stations might get an accurate report, but calling the school and using that's on their website is useless. Okay. Here we come to part 2. Okay. You know this, you guys know this already, my phone numbers, my email address, where I'm located. The only thing that's changed a little bit is my office hours. Here we go. And if you have a copy of the syllabus, within the syllabus is this page here with my office hours. My office hours, of course, are still in the red with the yellow highlight. This semester, I'm going to be Zooming all of my office hours, simply because I expect that, well, 2 reasons. The weather's probably going to be crappy the whole time. And also, I've only got 1 course besides these that I teach here, 1 course at New River, in which I have face-to-face students. The rest of them are all online. So I'm going to Zoom on the office hours. So you can zoom in at the same, it's not here, but at the same Zoom ID, meeting ID, as the one that you're connecting now. And during those times and days of the week, most of the time I'll be Zoomed in. If I'm not there, it's probably because I called away to do something else. But as usual, if you need a Zoom meeting at any other time, as long as I'm not occupied in that 1 class that I teach, then we can Zoom. I just need to know when to open up the Zoom meeting, and then we can solve any problems that way. Okay. So here's the schedule. And let me scroll up a little bit. I never did get that special controller that allows me to scroll from here. I had every intention to, but fate intervened. And let's see. All right. And have been working all during the winter break on this bright space thing, which is not ironed out yet. We can't connect bright space Zoom yet. And I've inquired, and I don't know why, that they don't have the Zoom tool built into Brightspace. And I haven't got an answer yet. Okay. So this is laid out similar to our first semester in that the material covered is based upon my general chemistry class at New River. But I've got your textbooks chapters correlated over here with mine. So when I say we're going to cover chapter 10, I probably should add here Brown 11 and 12. So that'll show you where that material is in your textbook. We'll probably look at maybe a little bit of safety items, but I don't think that's quite as important because you guys have already shown that you're safe in the laboratory from last semester. But today, we're just going to cover this discussion of liquids and solids after we look at the syllabus. And I should have highlighted these exams in yellow. I'm sorry about that. But these are the exam days here. I think there's 7 of them. Yeah, 7 exams with no final. So the 7th exam will be in the finals week. Okay, and we'll follow the same pattern. We'll have material 1 week. If we have to cover 2 chapters, let's see. Here we go. We have to cover 2 chapters. I could probably get those done in one session. Then we have, I split these into 2 sessions here, these topics, because these beginning topics, while they look simple, they can be a little bit complicated once we get into the weeds. So I give us a couple of sessions to cover those topics for our first exam. And then we'll have a review on the 4th of February, followed by that exam. And here we have lab experiments. So we're not going to have one next week. So that's when I'll distribute the hard copy for this one. And this will be a formal report. The second one will be a formal report. The third one will not. The third one will be hard copy, complete the hard copy and turn it in. And there's one other one. That one's a formal report. This one's a formal report. And this one's informal. I think, do I have the right color on that one? No, I don't. This one should have been colored red for informal. So we have 2 informal reports and the other 4 are formal reports. Okay. The grading scheme should be the same as last time. 80% from the exams and 15 for the lab reports and 5 for lab skills and lab notebooks. Now, if we have a whole bunch of snow days, I don't know yet how we're going to deal with that. Not without, now we still have access to Brightspace. We just can't Zoom through Brightspace, and that's a problem. But I can still, and I will add this, the course in Brightspace is going to remain under construction for the entire semester. So check back often. I'll be adding stuff along the way, trying to build it up. I couldn't get it completely built up. In fact, it's just bare bones right now, not much information there. And if you've been there, you already know that. But I will be adding things as we go along. I'm trying to stay 1 exam ahead, if at all possible. Okay. This stuff is not important for you unless you're just interested in mapping course objectives. Okay, you know about calculators. You know about zooming under our special circumstances. And there's your lab notebooks again. I didn't bring any with me today. I probably should have. In case you can't find any out, I'll do that next time. Regular exams, lab exercises, you know all that stuff. Bonus and extra credit. I don't have any special bonus projects this semester, but exams will probably have some bonus questions in it. And we'll work from review documents. All right, so I don't remember what I sent you guys. I know I sent you a syllabus and PowerPoints, I'm pretty sure. Did I also send you review documents?
Yeah, I think you did.
Okay, good. Because that's how we'll follow the same pattern as last semester with review documents that inform you about what I think is important and what you're likely to see on an exam.
Okay.
And this is the sheet with my schedule. It also has this Zoom meeting link. I don't think you can click on it from the document and get there, but you could copy and paste it in. There's no passcode that's required. You just put that in and you're in Zoom. Okay, part 3. The only relevant part of part 3 is the textbook and lab exercises. And you probably already got a copy of both of them. Okay. And that's more assessment stuff. That's my headache, not yours. Okay. So let's jump into chapter 10. Let's see. Yeah, it covers everything. All right. It's still not very good. I'll have to doctor that a little bit in the recording. But if there's anything that you can't see very well, let me know. And I'll try to get it to show up better. Okay. Chapter 10 is going to be a discussion of liquids and solids. That doesn't sound like much. That's a loaded topic right there. Because we're going to look at what makes liquids, and solids, and among other things. Let's see. Well, there's no table of contents for this one. What holds them together? You know, why are they liquids? Why are they solids? What can we learn about the chemistry of these compounds and elements based upon their physical state and how they react to changes in their physics? Well, when we talk about bonding in molecules, there are various types of bonding, but we can, for convenience, subdivide the bonding into 2 categories. Either the bonding that takes place inside the molecule or the bonds that take place between molecules. And we say intramolecular bonding is the bonds that hold atoms together. Now, for the purposes of this argument, unless we specify, we're generally talking about covalently bound molecules. And we will discuss, we're not leaving the ionic compounds out, right? But for now, when we say molecule, we mean covalently bound compounds. So the bonds within the molecule are the intramolecular bonds. They're what we normally think of as bonds. Whereas the intermolecular forces are those that are felt between molecules. And they can be placed on a gradient of strength. So if we talk about the intramolecular bonds, the strongest, of course, are those covalent bonds. Right? Once you get outside the molecule, then they tend to get weaker. And that makes sense, because if the bonds outside the molecule, between molecules, were stronger than the molecule's bonds inside, it would tear those molecules apart, and they wouldn't be molecules for very long. So, intermolecular forces are always weaker than intramolecular forces. Now, the best way to think of these intermolecular forces is in terms of electrostatics. In other words, differences in charges. Positives attract negatives. And as you already know, there's a gradient of charge distribution. You can have a complete positive negative charge if an electron, one or more electrons, is transferred from one atom to the next. Then you get a complete charge, positive, negative. But you can also get gradations in between. A slight transfer of electron density within a molecule will give one side of the molecule a partial negative and the other one's partial positive. And then when those molecules come in close proximity to other molecules, whether they're the same compound or not, you get the electrostatic attraction. And this is what we call the dipole. And the dipole means that they're separated charges. In other words, the molecule might be slightly negative on this side and slightly positive on this side. And then when they come in close proximity, if there's a negative side on this, it'll attract. That is a dipole. That's as opposed to an ion. A dipole has a positive and a negative, whereas an ion might be just positive or just negative. I guess technically we call it a monopole. And there are various strengths of these dipole-dipole interactions. And the strongest falls into a category called hydrogen bonding. And we'll flesh that out in a minute. Then there's weaker forces, we call them London dispersion forces. These are permanent. Relatively speaking, they're permanent redistribution of electric charge. Whereas London dispersion forces are instantaneous. They come and they go in microseconds. And then, I can't say this too often, intramolecular bonds are always stronger than intermolecular bonds. Okay, so how do we get these dipoles? The dipoles are produced by a difference in electronegativities between the atoms of a bond. So if you have, well, we'll use water, for instance. We know from last semester that oxygen is more electronegative than hydrogen. So it tends to pull electrons towards itself. And it develops a slightly negative charge. That little squiggle is a delta, a Greek delta, a small letter delta, as opposed to the big letter delta, which is like this. And we use that just to mean that it's a slight negative charge. It's not a complete transfer of electrons. And that would leave, on this side, a slight positive. And to be balanced, I guess I should put a 2 out here. But that gives you a dipole on this bond. And the way we represent that dipole is with an arrow. And we point toward the negative, like that. And then we mark this end as the positive. So that's an indication of a dipole in the bond. Okay? Now, that's for the individual bonds. We can also designate a dipole for the whole molecule. And for that, we have to do some vector addition. I don't know if I described vector addition for you yet, but it's a physics problem. Usually associated, physics students encounter a vector addition in terms of static forces. Like if you have an object here, and somebody's pulling on it with a force here, and they're pulling on it with a force here, what's the net force? Well, the net force is somewhere in between. right? It's like this, something like that. But you find the answer by vector addition. Well, we're not going to do vector addition here, but the explanation is that the dipole here, because the dipoles are both headed in that direction, for the whole molecule, the dipole would be like that when you add them together. So the whole molecule is polar toward the oxygen and negatively polar toward the oxygen, positive toward the hydrogen. And when you get them in close proximity to one another, you get something like this. Right? You get a slight bond. It's not a covalent bond. It's an electrostatic attraction between the negative and the positives. Right? That's why water is a liquid at atmospheric pressure and room temperature. If it were not for this bonding, then water would be a gas and we'd be in big trouble. Now, this is a dipole-dipole interaction, but it's a special kind. It's a very strong dipole interaction. And we call it hydrogen bonding. In order to have hydrogen bonding, you need two things. You got to have hydrogen bound to a very electronegative atom. It's either oxygen or fluorine, usually. Gives you this hydrogen bonding. So hydrogen fluoride or hydrofluoric acid, if it's in solution, will exhibit hydrogen bonding. Okay, just to check, which is stronger, intramolecular or intermolecular? Intra is inside, inter is between. So the stronger one is the intramolecular. And how do we know? For practical reasons. If that were not the case, then the molecules would be ripped apart. Okay, and that's basically what I'm saying right here. Now let's talk about this intermolecular bonding in terms of phase changes. The strength of the bond, the intermolecular bonds between molecules, determines whether that pure substance, water for example, is a liquid at a given temperature or a gas, or maybe even a solid. Right? So the stronger the attraction for a given temperature and pressure, the stronger the attraction, the more likely you are to see a solid rather than a liquid, or rather a liquid than a gas. The strength of that bond determines the phase. Now, if the strength of the bond is very, very high, then the melting point of the solid will also be high. It takes a lot of energy to break that bond if it's strong. Okay, so there are phases, gases, liquids, solids. And if you go from a solid to a liquid, as you add energy to the solid, you start to get vibrations in the molecules of the substance. And in the beginning, they just vibrate a little bit, add more energy and raise the temperature, vibrate more. Eventually, they vibrate so much that they break the intermolecular bonds that are holding the solid together. I say break. They weaken them significantly. Because if it goes from a solid to a liquid, there's still some interaction. It's just not enough to hold them in position to make a solid. So what it will do is it'll hold them just enough to maintain a given volume, but not a shape. And that's where you end up with a liquid. If you go from a liquid to a gas, then as you add more energy to that liquid, you break those bonds almost completely. Gas molecules interact very infrequently, and when they do, the interaction is weak because there's just too much energy there that overcomes the intermolecular attractions. Okay, This speaks to the density of solids, liquids, and gases. Now, this, in my opinion, this is a bad example. Because normally what you see with a transition from solid to liquid to gas is the density of the solid is greater than the liquid. It may not be much, but it's usually a little bit greater. And as you break the bonds and separate those molecules into liquid phase, you put a little bit more space between them, which expands the volume for a given mass. So that would decrease the density from solid to liquid. You'll notice that for water, it's the other way around, right? If you go from solid to liquid for water, the density increases. So the molecules are getting closer together for the liquid than they are for the solid. And I'll explain that in just a second. But this is true. If you go from liquid to gas, the density goes way down. You're taking up a massive amount more volume for a gas than you do for a liquid. Now, the rule of thumb is the volume increases 1,000 to 1 from liquid to gas. And that varies all over the place, depending on the substance. In this case, the ratio is about, oh my goodness, it's closer to 3,000 to 1. Anyway, why in this case does water defy the trend from higher density solid to lesser density liquid? Well, it has to do with the way that water forms a solid. And it goes back to the hydrogen bonding. As you decrease the energy of the liquid water, you slow down its motion, it has a chance for the intermolecular forces to interact more strongly between individual molecules. Then what you do is you set up a lattice for the solid. If you have, say, a water molecule, we get another marker. Say if you have a water molecule here like this, and then you have another one over here like this, then you get some hydrogen bonding there, and then you might get hydrogen bonding over here. And then you could form a ring structure. So what it does is, as you decrease the temperature and you slow those molecules down so they don't break the bonds, they tend to form a lattice that looks like a hexagon. So you have maybe a hydrogen here, an oxygen there, hydrogen, oxygen, hydrogen, oxygen, with hydrogen bonding like that. Okay? Now, obviously, you're going to have, well, actually, this might be a solid, and then you have another hydrogen here. This will be that type of bond, and then I have a solid here and a hydrogen over here. And let's see, this would be a solid here and a hydrogen over here. Okay, so you form that ring structure. Well, what that ring structure does, and there are hydrogen bonds out here too, is it opens this up. So ice, water ice, takes more volume for a given mass than liquid water, because liquid water allows them to collapse and move past one another, whereas the crystal structure of water expands and leaves this big gap in the middle. That's occupied space or unoccupied space. It increases the volume and decreases the density. That's why this trend reversal. Okay. But the moral of the story is, as you decrease the amount of energy, then you allow the molecules to get closer together and their density increases in general. with some exceptions like this one. Okay, how about the actual forces of a dipole-dipole interaction? It requires molecules with polar bonds, right? We've shown that before. You need polar bonds to cause a slight redistribution of electrons to give you a slight charge difference. And when the molecule then acquires a dipole moment, we call it. Moment is a physics term, which means a directional force, represented by that arrow. That represents a dipole moment. They line up in such a way that the positives line with the negatives and negatives with the positives. And with a dipole in your molecule, they just sort of, well, it's three-dimensional. But they line up with those electrostatic attractions. Now, in general, as a rule of thumb, so to speak, the strength of the dipole-dipole interaction is in the neighborhood of about 1% of a covalent bond strength. So they're a lot weaker, but they're still significant. And it depends on the temperature. If the temperature decreases, then the dipole interactions become more prominent. If you increase the temperature, then those dipole bonds are not strong enough to withstand the added energy. Okay. Oh, this is one of those situations. I'm sorry. This is a discontinued format in a video, so we can't watch it. That one either. There we go. Now, this is in words what I was trying to explain with hydrogen bonding. It's a very strong, relatively speaking, to other dipoles. Very strong dipole-dipole interaction. Requires hydrogen and a highly electronegative atom. I said oxygen and fluorine. Sometimes nitrogen is in there also. Okay. And there's one other item that I left out. When you have, we'll use water for an example. Right? When you have water like this, and we've done the, I think we've done the VSEPR model, and we've done the structures. You know that I was going to sneeze. You know that you have some lone pairs here. Those lone pairs also add to the negative character of that side of the molecule. Okay, so that makes it even stronger toward the negative on this side. And you get that from fluorine as well. Let's see. Fluorine is going to have, right, if we draw the Lewis structure, fluorine is going to be like that with those lone pairs. Nitrogen, let's see, ammonia. Like this, like this, like this. And it has a lone pair up there also. So this gives the negative side of the dipole a little more oomph. Negative, 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 because of those lone pair electrons. Okay. London dispersion forces. Okay. London dispersion forces are the weakest of the intermolecular forces. And like I've said before in past semester, and I'll say it again now, nature just does what it does. And we have to explain why, what it does and why it does it. Ideally. London dispersion force was invented or conceived in order to explain why you get a change in phase for some substances that you would not expect to have any attraction for adjacent molecules. Nitrogen is a perfect example. Right, like that. That molecule is balanced. Nitrogen and nitrogen, both same dipoles, both same electronegativities. So there's no dipole here. But if you cool it down, if you take the temperature down low enough, minus 195 degrees Celsius, it will turn into a liquid. So how do you explain that? The phase change that we're trying to describe in terms of intermolecular attractions. So how do you get an intermolecular attraction out of a nonpolar molecule? There has to be some other force at work. Now, granted, it's very weak because you got to get it really cold before the force takes effect. So that's where London dispersion forces come in. And that's the same with particularly the noble gases, right? You got to get them really cold in order to do the phase change. In fact, I think the coldest substance that's produced in the laboratory is liquid helium. It's about 4 degrees Kelvin, just 4 degrees above absolute zero. And in fact, when superconducting was all the rage, the only way that you could get a material to become a superconductor was to cool it down with liquid helium. Liquid helium. Then they did research and they developed substances that would become superconducting at higher temperatures. So then you could use liquid nitrogen. And that's how they cool down the superconducting magnets of the MRI units in the hospital with liquid nitrogen. Okay, so back to the London dispersion forces. So the explanation is that the electron density in a molecule, in this case, nitrogen, is always in flux, which means that it's not static. In other words, for an instant, a microsecond, you may get electron density redistribution like that. Very, very slight. This is even more slight than dipoles. It only happens for an instant. If there's a molecule of nitrogen close to it, this difference in charge will induce a change down here. This will attract electrons to itself and make this one negative and deplete that side. Now you have a difference in charge. At least for a microsecond, you get an attraction. Okay? And it tends to happen, the London dispersion forces tend to be more prominent in larger molecules because with more space, you have a better chance of getting instantaneous redistribution of electron density around it. So the evidence for that is the boiling point of gases, noble gases. Let me see if I've got a chart in here. I don't want to steal my own thunder. I'm looking ahead in a hard copy. Let's see. No. Okay, so I don't have the exact values. I don't have the exact values, but I can say that if we have noble gases like this, helium, neon, argon, krypton, and xenon, these atoms are getting bigger as you go down in the family. I already know this one is 4K, is the boiling point. I don't remember what these are. Oh, this one would be, well, let's see, what's 195? 273 and 195. That's 8. Let's see, 9 plus 16 is 7. 78K. Okay? So I know those two. But the trend is, as you increase the size of the atom, you increase the boiling point, which means the London dispersion forces are becoming stronger as you increase the size. And that's simply because with larger size, more volume, you have a higher probability of developing redistribution of electron density over a larger space and over maybe a longer time period. So the highest boiling point of this series will be xenon, because it's the bigger molecule, the bigger atom, I should say. Okay. Also, if you know anything about hydrocarbons, methane, ethane, propane, butane, like cigarette lighter, pentane, hexane, heptane, octane in your gas tank, on up into octane, nonane, decane, bigger molecules, diesel fuel, axle grease, coal tar. Those are bigger and bigger molecules. You get bigger molecules series that their melting point is much higher. So asphalt, it takes a lot of heat to melt asphalt because it's a bigger molecule and it's a nonpolar molecule. All the hydrocarbons are nonpolar. But as you get bigger molecules, you get stronger London dispersion forces. And that increases their melting points or boiling point, as the case may be. Okay. This just reiterates what I've said already. The stronger the intermolecular forces, the higher the melting points, the higher the boiling points. Now we're going to talk about some other physical changes that take place and relate them to these intermolecular forces. But for right now, we're talking about boiling points. Right. In this example, we're looking at carbon, nitrogen, and oxygen and fluorine. So across that second period, right, from carbon, nitrogen, oxygen, fluorine, as we increase if we go from left to right, carbon, nitrogen, should be oxygen in here or down here, and fluorine, we would expect to see the boiling point increase as we move to the right. The electronegativity increases, and that gives us more polar bonds. But as it turns out, water bucks the system because of its unique characteristics. It does have polar bonds. It's also shaped, bent, and it has 2 extra pairs of lone pairs. Whereas methane has no lone pairs. It is completely symmetrical. It's a non-polar molecule. So its boiling point is going to be very low. Liquid methane is very cold. Just ask Elon Musk, right, with SpaceX. They're firing up their boosters. Their Raptor engines use oxygen and liquid methane as their fuel. And it has to be cold. It's a cryogenic liquid. Okay. So which molecule in this example is capable of forming stronger intermolecular bonds? This should be easy. You look at the strength of the bond and the geometry, right? So nitrogen we've shown is nonpolar, whereas water is polar. It's not only polar molecule, it's hydrogen bonding capable. So the stronger intermolecular forces will be for water. Now, in organic chemistry, these are what's known as structural isomers. In other words, they have the same molecular formula, right? C2H6O. Same formula, but they have different structures. This structure gives you ethanol, the drinking kind. This structure gives you dimethyl ether. Notice this one's balanced, right? And any, I don't know, I think I said this last semester. Two things that you have to consider when you're looking at the polarity of a molecule. One is polar bonds, and the other is geometry. In this case, we have a polar bond there, and it's not balanced. It's imbalanced. There's ability for hydrogen bonding here. Whereas this one, oxygen is more electronegative than carbon, so you should get a dipole this way and a dipole this way. They cancel each other out. Dimethyl ether is nonpolar. So how do we compare the boiling points? Which one has the stronger attraction between molecules? Ethanol. So ethanol would have the higher boiling point. It takes more energy to break those bonds than ether does. And you can prove that to yourself. If you have two bottles in the back of the lab or the lecture hall, one's got ether in it and one's got ethanol in it. Open the caps. How long does it take and which one do you smell first? You get ether first because it vaporizes quicker. The forces holding it together are much weaker. Okay. All right, now this takes us back to ideal behavior in a gas. So remember, I hope I've told you this before, but I'll tell you again. Gases behave ideally under what conditions? High temperature, low pressure. Under those conditions, the individual molecules or atoms, whichever the case may be, in a gas, do not interact. Right? High temperature means that there's too much energy there for the intermolecular attractions to be significant. And under low pressure, that means there are too few molecules in there to make a difference. There are too few interactions over a time period. So which one of these would behave more ideally? The one that has the weakest attraction between molecules. And that would be nitrogen, because it's a nonpolar molecule, whereas carbon monoxide is slightly polar. Carbon and oxygen have different electronegativities. You're going to get a dipole for that molecule. So this one is the more ideal. And I offer an explanation down there. All right. The liquid state. Liquids are, for all intents and purposes, are incompressible, or at the most they have low compressibility. And what does that basically mean? When you put a liquid under pressure, there's not much space for the molecules to approach one another and decrease the amount of space between them. Solids, they are very resistant to, they're essentially incompressible. Liquids are only slightly compressible, and we know that. Right? Nature does what it does, and we have investigated it and found that the density of water at great depth in the ocean, like 2-3 miles down, is much higher than it is, measurably higher, I should say, measurably higher than the density of water at the surface because of that added pressure. So liquids are low compressibility. They're not rigid, obviously. Compared to gases, compared to the gas of that particular compound or element, they have very high density by comparison. The rule of thumb is what, 1,000 to 1 difference in density. Surface tension. Surface tension, we need to define it first. Surface tension is the resistance of a liquid to increase its surface area. So in other words, if you have a drop of liquid, then it's going to be difficult to make that drop bigger. Another way to look at it is in a sheet of liquid. So if we have a container and we have a liquid here, if you look internally, you have molecules here, which I'm representing by a single circles. Then you have molecules at the surface. Right? Now, there are attractions here between these molecules. And for the molecules that are internal to the liquid, the attractions are balanced all around. That tension, the force of attraction is balanced. But on the surface, you've only got attraction between the surface molecules and those below them. So think of it this way as a pie. The force of attraction for individual molecules is the same, no matter which one you're looking at. So if you've got them at the surface and they have to have that attraction balanced somehow, the strength of attraction has to be distributed over a smaller area. So you get a stronger bond between these molecules at the surface than you do between molecules internal to the liquid. That's surface tension. Now, we know surface tension is real. You can use, in fact, I did this as a kid. I saw it on some TV show. You can take a needle and magnetize it. You just need a strong magnet and you pull it across there in the same direction until you get a magnetized needle. And then you set it in a pool of calm water, right? Hold it by the tips. Don't push too hard. And just set it on the water and it'll float. And it'll also orient itself to the North Pole, the North Magnetic Pole. Okay, why does that needle? The needle is denser than water. It shouldn't sink, right? Right? Anything that's more dense than water should sink. But there is sufficient surface tension force to hold that needle up. We see it in nature. Insect called water skimmers. They have 6 legs and they just sit on the surface of a calm pool of water and they just scurry around. They distribute their weight over 6 legs using the surface tension of the water. Now that we've defined that, let's look at relative surface tension among different types of liquids. We find that the surface tension for liquids that have the high surface tension is due to stronger intermolecular forces. So the stronger those forces between molecules, the higher the surface tension. For instance, the strength of attraction. Now, this kind of deviates some because I'm going to talk about mercury. Mercury is a liquid at room temperature, and the strength of attraction between mercury atoms is very high, as opposed to the attraction between water molecules. So mercury, you can set something that's denser than mercury on top of it, and it will support a lot of weight relative to the same type of experiment with water, because the surface tension in mercury is higher than water. And that's because the intermolecular forces between the mercury atoms is higher than it is in water. And I'm sort of stretching the definition here because mercury is a metal and it has a different type of bonding regime. It's called a metallic bond. So forgive me for jumping off this boat into another boat for a little bit, but the same principle applies. The stronger the intermolecular forces, the stronger the surface tension. And surface tension can't be measured. So that's how we get a handle on the intermolecular forces for different liquids, by measuring their surface tension. Another characteristic of liquids is what's known as capillary action. And by definition, a capillary is a very thin tube. Usually we make them out of glass because it's easy to work them and make very thin capillary tubes. The capillary action is what happens when you immerse the tip of your capillary in the liquid, and the liquid tends to rise in the capillary. So it's higher than the surrounding liquid. So what that tells us is there are forces at work here that are drawing that liquid up into the capillary. Well, one way to rationalize, one way to approach this problem is to view it in terms of opposing forces. These intermolecular forces can be subdivided into adhesive forces and cohesive forces. The cohesive forces are those that attract the liquid molecules together. And the adhesive forces are those forces that are experienced between the liquid molecules and the walls of the capillary. So, in this case, if we have a capillary and a liquid, like that. I made my capillary big so I can draw on it. The liquid starts off here. Let's say it ends up here, like that. So what causes it to go that high? Well, there are forces attracting the molecules of this liquid together, right? And they would tend to pull that liquid down because it wants to stay together. Surface tension. Keep the surface area as small as possible. But there are forces between the liquid molecules and the surrounding and the walls of the tube that are pulling it the other way. So we have a balance. Those adhesive forces are fighting the cohesive forces. And as adhesive forces pull on those molecules to go up the capillary, those molecules are also pulling against cohesive forces of their neighbors on the other side. And at some point, there's a balance. The adhesive forces and the cohesive forces exactly equal one another. And that's what determines how high the capillary rises in the tube. Now, one thing we've noticed in aqueous solutions, pure water or solutions in water, when we try to read the volume on a pipette or a burette, we notice that they form a meniscus like this, a curve. Well, if it's a concave meniscus like this, we can assume that the adhesive forces are higher than the cohesive forces in an absolute sense. Right? It's true that the overall forces are balanced at this level, but at the intrinsic level, the adhesive forces are greater than the cohesive forces. On the other hand, if the meniscus is the other way, like this, a convex meniscus, we can surmise that the cohesive forces are stronger than the adhesive forces, right? Because the internal is higher than the surface. And that would be the case for mercury and glass. Now, this all depends on the nature of the liquid and the nature of the capillary. You could get something different here if you have a different capillary material. Or, actually, with some capillary materials, it could be straight across, in which case the cohesive and adhesive forces, we may assume, are equal at the molecular level. Okay. Oh, question. Which force dominates alongside the glass tube, cohesive or adhesive? Well, the cohesive forces dominate for this convex meniscus. For the concave meniscus, the adhesive forces are dominant. Okay. Another characteristic of liquids that's dependent upon intermolecular forces is viscosity. What is viscosity? Viscosity can be a quantitative expression of the resistance of a liquid to flow. How willing is it to flow? And there are a number of ways to determine it. You can have a penetration probe that determines viscosity, a weight and a sharp point on the end, and you drop it into a liquid, see how far it goes. Or, more commonly, you have a liquid that is in a container, and you see how fast it flows through a small orifice. Right? The more viscous liquid will flow more slowly, and the less viscous will flow faster. Okay? The viscosity is directly proportional to the cohesive, the intermolecular forces holding that liquid together. So if you increase the forces holding it together, viscosity increases with increasing intermolecular forces. Large intermolecular forces cause high viscosity, so they are directly proportional. So, usually, the more complex the molecule, or the larger the molecule, the more viscous it is. And we can say that about those hydrocarbons, right? Octane, gasoline in your tank is not very viscous. Whereas axle grease, which is a bigger molecule, is more viscous. And asphalt wouldn't be measurable. Now let's look at solids. Right? What kind of solids can you have? Well, we can subdivide solids into two groups. What we call crystalline solids, and the other is called amorphous. A is the Greek prefix that means not. And morphous is also a Greek word, a root word that means form. So they have no form. Amorphous solids. And there's really more to it that than that, based upon the molecular structure of a substance. So let's take crystalline first. Crystalline solids have an ordered structure. In other words, you can sample the crystalline solid at any size you want, and it will have the same structure inside. In fact, you can sample smaller and smaller and smaller and smaller until you get to a certain point where you have a unit of which the crystal is composed, the larger crystal. And you just repeat that unit over and over and over again, and you get a larger crystal, but it's still the same structure. That's called the unit cell. Now, amorphous solids have a disordered structure. They do not have repeating units of any kind. Glass is a good example of that. Most glasses, I should say. There are some glasses that are produced in term that will generate crystalline structure, but they're special use, special cases. In fact, there's one school of thought that says glass is a supercooled liquid. You know, maybe it is, maybe it isn't. Okay, crystalline solids can be described in two different ways that are mutually supporting. Okay, the first way is in terms of the unit cell. Right? The smallest three-dimensional repeating unit in a crystal is the unit cell. And you can build up your crystal with these unit cells. The other way is to use a model called the closest packing structure. And this is like, if you dump a bunch of marbles into a container and shake them around a little bit, what are they going to do? They're automatically going to organize themselves so that the marbles fall into the spaces below them. They don't sit balanced like this on top of one another, right? They slide down into the space between them. That's what closest packing means. Now, in some cases in nature, you do get, it depends on how the crystal forms, you can get layers that sort of defy the packing structure. And we'll describe those in a minute. Okay, these two methods may be considered two sides of the same coin. In other words, you can relate them. And we're really just going to skim across the surface to try to get a rudimentary understanding of what this type of information tells us about solids, crystalline solids. But if you know one, very often you can infer the other one. Or if you know this one, you can infer that one. Okay, so if we take the unit cell approach first, there are a number of different unit cells that are possible, but these are the three most common, right? The first unit cell is the simple cubic. So the atom, the metal atom, the molecule, whatever the case may be. And for simplicity's sake, it's easiest to describe these structures in terms of metallic atoms in these positions. So the simple cubic has one at each one of the corners, right? So 2, 4, 6, 8. So we have 8 occupants at each corner. And this structure, if it's repeated in a lattice, looks like that. Notice that you have a cube here, but this cube shares occupants of that other cube. And that's important, right, for doing our calculations. And then in reality, you actually have this space filling model in which that cubic, simple cube, is actually represented by only a portion of each one of these atoms, and they touch one another. That's what defines their limit. this ball and stick model is not quite accurate. This is the better model, where you have a space filling model, and you see that the atoms are touching one another in this simple cubic. Okay? The next possibility is to keep those corners occupied and then stick one in the middle. So now we have 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 occupants of that unit cell. But when you put it in a lattice, you find that this central occupant here is the only one that's 100% in that unit cell. The other occupants have to be shared among the other lattice members. And if we look at the space filling model, we find that here we have an internal occupant right here. And what that does is it forces these others apart so they do not touch. The other possibility is we have, the third possibility is we have the corners still occupied, but now we have another occupant for each of the faces of the cube, right? And how many faces does a cube have? Well, think of a dice. It's a die. Dice is plural. A die with corners, and how many numbers are in a die? Right? 1, 2, 3, 4, 5, 6. Right? You throw 2 dice, and you get both ones. That's snake eyes, right? Well, in that case, the faces are occupied with another one of these. That means that these are shared among 1, 2, 3, 4 other cubes. Whereas this one is only shared with the face next to it. So it's half in one and half in the other. And the space filling model looks like this again. There's nothing in the center. These are all faces. These are all on the face. And you find that only 1/8 is occupied here, but 1/2 is occupied there in that unit cell. Okay. All right, so how do we get direct evidence of the spacing of atoms in a crystal lattice? Well, as it turns out, we know about how light behaves as it passes from one substance into another. Say if it goes from air into glass. Different densities of substances that are transparent to light will bend the light. So if the light comes in, and say this is glass, and this is air, right? That's our interface. Then as the light beam comes in, it's bent like that, away from the more dense liquid, the substance. So that's what's known as a ray trace. This is a ray, and as it approaches, this is the normal, right? Because that's a right angle. And then it comes in at an angle here, and then the angle here is smaller than that angle. So it bends toward the more dense, normal. Okay. As it turns out, well, that's refraction. Diffraction is, I think diffraction is what explains this one better. So these layers of atoms in the crystal structure serve as focal planes, so to speak. So as the light enters the crystal, it's bent, but it's bent differently. Well, actually, no. Let's see. I think I've got Here we go. This is a better explanation. So here's the surface of the crystal. And if this ray comes in, it's bounced off like that. And if this ray comes in and it's bounced off like this, off of that surface, right, in the crystal lattice, we've got them stacked here, then the concept here is interference. How do these waves interfere with one another? Notice that this one is at the same, it's the same, it's lined up, so to speak. The crests and the troughs are lined up. That's called positive interference. When that happens, then you get a strengthened signal that can be detected, right? You fire X-rays, in this case, at the substance, and then you rotate your detector until you find the angle where you get the maximum reflected energy. That's because they're reinforcing one another. They're positively interfering. If they're negatively interfering, then you know you're not at the right angle. And the angle that you measure is here, which corresponds to the same angle here. Okay? And with a little trigonometry, you can calculate, based upon that angle, the spacing between the layers. That's the Bragg equation. Okay? Bragg and his son, I forget their names right now, developed this theory. And all you have to know is the angle that you measure for maximum and the wavelength of the light. And as you rotate to find the angle, the first one you come to will be n equals 1. That's an integer, 1, 2, 3, 4. And it pertains to the order. Right, so I'm not going to get into that much detail. But first order would be the strongest. Second order would be weaker. Third order would be weaker still. And you can calculate the distance between the layers. And you can deduce from that what type of crystal structure you actually have. I use this for working with clays in soil. The process is long and laborious, separating the clays from all the other particles in the soil. Once you get them separated and plated on a glass slide, just like a microscope slide, then the clays are in plates. So they tend to float down in the liquid and they line up like this. So when you fire X-rays at them, you're looking at the distance between the layers in the clay. And you can use that information to deduce what type of clay it is. Okay. So with this information, we can determine the distance between the layers of our crystal. Now, the thing about it is, that works in 2 dimensions, right? But you can also get 3-dimensional information from firing X-rays at a crystal, right? Here we go, fire X-rays at this crystal, and it produces a diffraction pattern. Now, it's more difficult to deduce anything from this, but over time and experience and calculations, you can deduce what type of unit cell is in that crystal based upon its diffraction pattern. This type of technology was used to deduce the structure of the DNA molecule. Now, credit was given to Watson and Crick, a Nobel Prize for that. But the labor was attributed to a young woman who was there. I don't know whether she was a research associate, I think so. She did all the legwork for it and much of the interpretation. But she didn't live very long. She died of breast cancer at a young age. So they got the Nobel Prize for it. But be that as it may, in order to make it work for DNA, they had to get DNA into a crystal structure because this only works with crystalline solids. That was the real problem with DNA. Okay. There are several different types of crystalline solids, and it just depends on what forms the unit cell. The ionic solids are formed by the crystal structure is set up in such a way that you have a balance of charges. So with sodium and chlorine and sodium chloride, the balance is 1-to-1. 1 sodium, 1 chlorine. Now they're different size ions, so that makes a difference also. But the ionic balance is what determines their unit cell. Then you have molecular solids, where you have these discrete molecules, like water. What type of crystal structure does it form? Well, we found that it formed that hexagonal structure. Or carbon, right? Carbon can assume several different crystal structures. Carbon graphite forms layers, hexagonal, covalently bound hexagonal structures in a layer, and then they lay on top of one another. And then the bonds between them are those weaker intermolecular forces. That's why graphite is often used as a dry lubricant, because they slide past one another so easily. And you don't need a liquid in there. And that's good because liquids tend to accumulate or trap dust. And then there are three-dimensional crystal structures for carbon that produces diamond. Okay, so you can have ionic solids, you can have molecular solids, discrete covalently bound molecules at each of the points of the lattice, or atomic solids, where you can have lattice points that are occupied by individual atoms. And that's usually what we're talking about with metals. Okay, let's see. Which type are we talking about here? I think I've got it. These are different types of forces holding these together, these crystal structures. This is water ice, right? That's why snowflakes have a hexagonal structure, because of this internal arrangement. This is an ionic solid, sodium and chlorine. Sodium is the smaller one, right? Because sodium is a positive ion, it's lost an electron, makes it smaller. Chlorine has gained an electron, makes it bigger. And then we have the diamond as an example. Okay, this is a covalently bound atomic structure. This is ionically bound ionic solid. And this is a molecular solid, which is held together by hydrogen bonding. Okay. Now, if we lay this out on the table, we find that these are all atomic solids. These are molecular solids, and these are ionic solids. So the atomic solids can be of different types. Right? We can have metal atoms bound together. We can have non-metal atoms, which is the case for diamond, carbon. And then we can have 8A atoms, which is the noble gases. And they're bound together by London dispersion forces only. That's the only possibilities they have. Okay, for molecular solids, you're looking at dipole, and London dispersion forces. And ionic solids, of course, are ionic forces. Now, what I failed to mention earlier is for London dispersion forces, they are always present in every solid and liquid. London dispersion forces are always present. Now, whether or not they are significant in the bonding is the other question. Because if there are dipoles around, they overwhelm the London dispersion, and you can essentially just ignore the London dispersion forces. But if the dipoles or ionic bonding are non-existent, then the London dispersions are your only way to get those intermolecular forces in place. Okay, we talked about the unit cell, and we sort of transitioned over into the closest packing description when we talked about the Bragg equation, measuring the distance between lattices. And like I said, the unit cell and the closest packing are opposite sides of the same coin. So they are related. So if we gain information from one, we can infer things about the other one. Now, in this discussion, we're going to stick to closest packing of metal atoms. It seems that it really does simplify things a lot. And at this level of chemistry, that's probably a good thing. Keep it really simple. We're talking about metal atoms. And there are assumptions that have to be made. In this case, we're assuming that these metal atoms are all uniform in size and shape, and that they all behave as if they were hard spheres. Now, we know that's not true, but simplifying it in those terms, these assumptions, makes it easier to develop our understanding in terms of closest packing models. And these spheres that we assume are packed in layers, and they can pack in certain ways. Now, I think I have a video. Let me see. I hope it made it into this version. Well, maybe not. Let me see. We'll keep our fingers crossed, because I've got a video that does a pretty good job of explaining this stuff. And I'm afraid that I don't. Okay. Think of your spheres in terms of layers. And then the way we've got it set up here, looking down from the top, you've got this layer down here, the yellow spheres. Okay. And the yellow spheres can be laid on top with another layer of spheres. So this is the A layer, and then the next one up is the B layer. And the B layer fits some of the spheres into these voids. Not all of them, right? Because we're missing one right here, and we're missing a space right here. There's no sphere fitting in that space. But we do have one here, here, here. And this is A layer, this is B layer. Now, if we put another layer on top of that, notice that the next layer up can be superimposed on that first layer. So now we've gone A, B, and we're back to A again in terms of its occupation of physical space. This layer is now got A, B, A. So this type of closest packing we say is AB, because of the way they stack together. Now, we mentioned 3 different types of unit cell. There is a third one that describes this type of packing. It's called the hexagonal unit cell. Or this whole scenario is called the hexagonal closest packing. Now, I wish I had that video because it gives you some three-dimensional images that describe the hexagonal. So if you look at these in terms of, you draw lines connecting these things, they will draw out a hexagonal shape in this closest packing model. And that's where the hexagonal unit cell comes from. So at this time, it might be just easier to say, all right, if you have a hexagonal closest packing, an ABA layer, ABAB, then you have a hexagonal closest packing with a hexagonal unit cell. In this case, the arrangement of atoms is in such a way that when we get the A layer and the B layer, now this blue is these, then we lay another one on there. This third one does not overlap either one of the A's or the B's. So now we have a C layer, ABC. But when we go back to the fourth layer, it is superimposed upon the A layer. So now we have ABCA. And that type of packing is the cubic closest packing, is what this is called. And it relates to our unit cell in terms of face-centered cubic. So this one is one that we've been introduced to before. The hexagonal was one that we didn't see before. Now this one we can relate to the face-centered cubic. Right? So you have the 6 points of the cube occupied, and then you have one on each face. 2, 4, 6, 8. 8 corners and 6 faces. And that's what the cubic closest packing relates to in terms of the unit cell, face-centered cubic. Okay. In this case, we have a hexagonal closest packing. And let's see. You know what? Hexagonal closest packing, ABA, and they're saying it relates to this one, which is also face-centered cubic. So how do we get face-centered cubic out of both of them? This one's face-centered cubic, cubic closest packing. But if we go back, this ABAB is hexagonal unit cell. But this says that ABA is also face-centered cubic. I'm stumped. I can't explain that. Why you can end up with the same unit cell in this term based upon that. So what that tells me is if that's true, then you get more information about your crystal structure by going closest packing model than you do this unit cell. All right, suffice it to say is I'm not going to test you any harder than I can understand myself. All right, let's move ahead and see if it makes any more sense in subsequent slides. Sometimes it does work itself out. All right, this cubic closest packing, which is ABCA, forms a cube here, and that relates to a face-centered cubic here. We can also look at the packing strategy in terms of coordination number. That is, how many other members of the lattice structure are in contact with one of the atoms. If we look at this atom, and in both the cubic closest packing and the hexagonal closest packing, they each have 12 closest neighbors. Right, so if you look at this one, we find that we're surrounded by 6, and then we have 3 on top and 3 on the bottom, and they're all touching that 1. That's required for a coordination number of 12. We have 6 here, 3 there, 3 there. In this example, it looks to me like we're looking at hexagonal closest packing, right? Because it's ABA, not ABC. So they're using that one as an example here. But they're telling us that both of them, both the hexagonal and the cubic, are coordination number of 12. Okay, this is a little more easier for me to follow, and hopefully it will be for you too. If we look at the unit cell, then how many atoms are actually associated with that unit cell? Remember, I referenced earlier that atoms were shared among cells as you build out the lattice. So how many belong to one unit cell? Well, rather than go to this one right away, let's look at the ones we've described so far. Right? So there's your cube. If you have 1 at each corner, right, you've got to share this one, and then you've got another one over here, and then you've got one on this face and this face, and then you've got one in the corner here that goes that way, and then you've got a couple on the back side. Let's see, 1, 2, 3. There should be 8 of them. Right? There should be 8 cubes attached to that one corner. So what that means is we only get an 1/8 of that atom contributing to that one unit cell. It's easier to see if we have a 3-dimensional model, but I didn't bring one with me. So, okay, for the unit cell, let me redraw that cube. If we have 8 corners occupied by an 1/8 of an atom, that means that the simple cube equals 1 atom. Because we got 8 atoms and only 1/8 per cube. If we put 1 in the center, then we have the body-centered cube, and that's 1/8 plus 1 in the middle, which is 2. Okay? Then if we have the face-centered, then we have 1 from an 1/8, right? And then how many do we have on the faces? We've got 1, 2, 3, 4, 5, 6. We have 6 faces. And we have half for each face. So a half of 6 is 3. Right? So the total is 4 atoms. Okay, so for the simple cube, that cube represents 1 atom, body-centered 2 atoms, face-centered cube is 4 atoms. And that's what this one is showing us. Right? 4 atoms contribute to that one unit cell. So simple cubic is 1 atom, face-centered is, oh, we left out the body-centered in this graphic. Okay. Now, what does that mean to problem solving? when you're trying to solve a problem? Well, sometimes you want to know, you can calculate the density of a metal based upon the knowledge of its unit cell and its molecular weight, or its atomic weight. So how do we do that? Well, first of all, you need to know the size of the cube, right? Because that tells you the volume. What size is your cube? In order to do that, you need to know, since it's a cube, you just need to know the edge length. How long is the edge? And then it's the edge cubed is the volume of that cell. And if you know the volume of the cell, plus you know how many atoms are located in that cell, then you can use the molar mass of the element and the number of atoms in a cell and the volume of the cell. You can calculate the density. As it turns out, those calculations are very close to measured densities for these. So we know that's confirmation that we have surmised the correct unit cell structure for that element. Now, in this case, simple cubic. What's the relationship between the radius of the metal atom and the length of an edge of the unit cell? Let's see, do we have a picture? No, we don't. Okay, so if we do it like this, and we use a space filling model, right? We'll just do it from here. Like that, like that. The space filling model says that these guys are touching. Right? So the edge length is the radius of the atom times 2. Right? Here's the radius of the atom times 2. That's simple. So now we know the edge length of that cube is 2r. It becomes a little more difficult when the atoms don't touch on the side of a cube. Then you have to use a little bit more trigonometry, actually geometry, to determine the edge length. In this case, the face-centered cube separates these guys some more, and it puts one in the center of the face. So we have a radius here, we have a radius here, and then we have another one like that. Right. So that diagonal is 1, 2, 3, 4. The diagonal, let's say this is A, this is B, and this is C. So A to C here is equal to 1, 2, 3, 4. 4 times the radius of the atom. Okay, well then, if we know this diagonal, and this is a right angle, and these are equal in length, then we can use a little Pythagorean theorem and find out how long that x is. Okay? Because this length, 4r squared, is equal to x squared plus x squared, right? A squared plus b squared equals c squared in the Pythagorean theorem. Right? And we can calculate what that x is. And as it turns out, the length of that edge is r times the square root of 8. Okay? Let's see. That was face-centered cubic. Are we going to do body-centered? Yeah, body-centered. So with a little bit more effort, the body-centered cubic unit cell tells us that the edge length is the radius of the atom times 4 divided by the square root of 3. And we use a similar procedure. In fact, I have handouts that I haven't put up in Brightspace yet. Let's see, we're coming up on 3 o'clock. 3 o'clock. 2:45, 3. Okay, 3 o'clock is when we normally start the lab. And let me see how many more slides we got, if I've got time to talk about it. Yeah, I better not. Suffice it to say, a little bit of trigonometry and geometry, and you can prove it to yourself. And eventually I'll have these things up in Brightspace where you can go look at the documents. So I've got an explanation for how to determine that. As it is, that information should, let me check. Those values should be in the review documents. And take just a second to see here. Yes. I've only got the body-centered cubic. The body-centered cubic is given in useful information. This one, you might have to memorize. Face-centered cubic is just r times square root of 8. But the body-centered cubic is r times 4 divided by the square root of 3. Okay. So here we're going to use knowledge of the crystal structure of silver to be cubic closest packed structure. And that produces a face-centered cube with a unit cell that is 409 picometers on the edge. So actually, okay, so we know the edge, we can determine the radius of the, what? We don't need to determine the radius of the atom because we're looking for density. What we need to do is say how many atoms are in that unit cell. And then we can determine the volume of the unit cell with that edge length. So we eliminated the process of calculating the edge length from any other information. So in this case, we calculate the density to be 10.5 grams per cubic centimeter. How did we do that? Well, I can think of using the measured density and the calculated density to confirm whether you've made assumptions correctly in the size of the unit cell. If you come up with a calculated density that's different than the measured density, and maybe your assumptions here are wrong, and you need to go back and try something else. Okay, what we do first is say that there are 4 silver atoms per unit cell, right? Because it's a face-centered cube. Right? We did that calculation earlier. So with 4 atoms per unit cell, and the volume of the unit cell is 409 picometers cubed, right? Or 6.84 times 10 to the 7th picometers cubed. Now, if we're going to express the density in terms of cubic centimeters, we need to convert this to cubic centimeters, which is simple dimensional analysis. There's no big mystery there. You just have to know what's a picometer and what's a centimeter. How are they related? Then, since we know the density is mass divided by volume, we need to know the mass. So with 4 atoms and with this molar mass, like grams per mole, we need to convert atoms to moles in order to cancel the moles and gives us grams. And that would be the numerator part of the density calculation. So if we multiply this times this, that cancels the moles, and it also cancels the atoms and leaves us with grams. And this is the cubic centimeters we just calculated, and that's where we get the density. And the calculated density is equal to, in this case, exactly equal to the measured density of silver. Okay. Now, I mentioned metallic bond earlier when we were talking about mercury and the cohesive versus adhesive forces. There are a couple of models that have been proposed, probably more, but for our purposes, we're going to focus on these two. The electron C model is the earlier one, and then the band model, which is derived from molecular orbital theory. So this is probably the current model. The electron C model for metal bonding simply said that the nuclei, the positively charged nuclei of metal, were embedded in a sea of electrons. Okay, and these valence electrons, and we're limiting our C to valence electrons because they're the ones that are easily translocated throughout the metal. But that had some serious shortcomings. Obviously, it would be unable to calculate energies, transition energies of any kind. The molecular orbital model, on the other hand, picks up with the same concept that we use molecular orbital model for molecules, covalently bound molecules. And it says that all those electrons occupy orbitals in this entire structure that are derived from the original atomic orbitals of their valence electrons. And as it turns out, when we do the calculations, which you can do, you probably need a supercomputer to do it for lots of orbitals. But the molecular orbitals then are structured in such a way that from one metal atom to the next metal atom, the difference in energy between these outer molecular orbitals is extremely small. It only takes a slight push, and that electron can change its loyalties from this atom to that atom. That's why metals are very good conductors of electricity. There's not much holding them back. They can jump from one molecular orbital to the other because they're so close together in energies. I think I have a model here. Yeah. So if we have two atoms, the molecular orbitals are going to be far apart. If we have four atoms, they're going to get closer together. More, closer together. By the time you get to a mole of metal atoms, their molecular orbitals are virtually continuous in energy. Now, another way to think about this in terms of molecular orbitals is the filled molecular orbitals versus the empty molecular orbitals. Often referred to, I think the LUMO is the lowest unoccupied molecular orbital, and the HOMO, which is the highest occupied molecular orbital. So this is the highest occupied molecular orbital here, and this is the lowest unoccupied molecular orbital. And the real key to solving the problem is how close are these together? And in metals, they're very close together. So you can move an electron from this filled molecular orbital into this empty one, and it can be over here next to this other atom in short order. Very little energy required to move it. Okay. So now let's jump to the topic of alloys. What's an alloy? An alloy is another word for a metal solution. Two or more metals mixed together, forming a solution, a homogeneous mixture. And alloys can be subdivided into roughly two types. One is the substitutionary alloy. That's a case in which the primary metal, what we would call the solvent, is mixed with a solute metal, and the solute atoms displace the solvent atoms in the structure. They substitute for them, right? Perfect example of that is brass. So brass is an alloy of copper and nickel. So the nickel atoms substitute for some of the copper atoms in the mixture. That's a substitutional alloy. The interstitial alloy is one in which the alloying material, the solute, actually fits into the gaps between the closest packed atoms. So there's no substitution of the alloying the solute into the solvent. It actually goes into the spaces between the atoms, so they don't have to move at all. And the best example of that is steel. So you have iron packed like that, for lack of a better. I'm just trying to illustrate the space. We got a space in here. So the only thing that'll fit in there is something that's really small, right? And we put carbon in there. That's an interstitial alloy, steel. Now, there's certain types of steel, like chromium steel, stainless steel, that are both types. They have the interstitial carbon in there, but they also have the chromium substituting for many of those iron atoms. Okay. And this is the artist's idea of substitutional versus interstitial. All right, we got another video that's not working because it's no longer supported. Network solid. Let's see, carbon. You know, they're probably talking about carbon here. So this network solid is a three-dimensional, covalently bound solid of carbon, diamond. And ideally, if you look at this allotrope of carbon, diamond, and if you were small enough, you could start at one side of the crystal, and if you follow the bonds to neighboring carbons, you could go all the way to the other side and never have to step out into open space. You'd be on the carbon or on the bond all the way over. It's like a single molecule if there are no flaws. Whereas the graphite is a network solid that has hexagonal plates here and here, and the attraction between them are intermolecular forces. Now, they would have to be London dispersion forces in order to hold them together because there are no dipoles here. So the forces holding them together are very weak. That's why they make good lubricants, because it doesn't take much to push one past the other. Okay. Now, what does this molecular orbital theory tell us about the conductivity, the electrical conductivity of these solids? Well, for metals, the highest occupied molecular orbital is just a gnat's hair away from the lowest unoccupied molecular orbital. So a little bit of energy can move the electron into this space, and it can shift over to the next atom and do the same thing. So metals are very good conductors. They have very low resistance to electrical conduction. Whereas diamond, when we look at the molecular orbital model for diamond, we see that the highest occupied molecular orbital is a long way in energy from the lowest unoccupied molecular orbital. So it takes a lot of energy to get that electron to move into this level so it can go to the next atom. That's why diamond, and in fact, that's the way the jewelers measure the stone. One of the ways, I should say, one of the ways that jewelers measure the stone to determine if it is really a diamond. It should have very, very low resistance. In fact, this is not just electrical conductivity, but it's also thermal conductivity. Thermal conductivity is also related to the movement of electrons. And if they check the thermal conductivity of your stone with a little device, they can tell you whether it is a real diamond, because its conductivity will be very low if it's truly a diamond. And they have numbers that go along with it. It's quantitative. Okay, here's another. Oh, this is graphite. Remember when we were talking about sort of a hybridization of the two theories of the hybridization model for carbon versus the molecular orbital. Well, the molecular orbitals we can see in terms of how this structure is covalently bound, but the overlap of these p orbitals is more along the lines of the hybridization model. And we get this pi system. These are p orbitals that form the pi bond. And this is the pi system that develops in the graphite. Okay, we're coming down the wire here. Ceramics. Let's see. No, I'm not quite done. Sorry. So what is a ceramic? I had a friend who wasn't really, I think he was on my committee, an advisor on my PhD committee. And I would discuss my various laboratory techniques that I was using in my research. And I would say, how do I explain this type of extraction of the soil in terms of its atomic value? And he said, it's operationally defined, which means it's whatever you want it to be. So that's the way I look at ceramics. Ceramics have certain physical and chemical characteristics, properties, but it's difficult to relate them directly to the underlying structure. There are some similarities, don't get me wrong, but ceramics are all over the place. A ceramic is made of non-metal materials, right? So it's made of stuff on the right-hand side of the periodic table. That's true. It's usually very brittle, and it's extremely resistant to heat and chemical attack. Okay, that's why ceramics of a certain type were used on the space shuttle as a heat shield, and why they're still being used on Elon Musk's Starship. If you look at videos of the Starship, you'll see these hexagonal panels, black hexagonal panels on one side of his Starship. They're made out of ceramics. They're heat-resistant ceramics. They're typically made from clays, right? And that means that they're essentially silicates of some kind. Clays actually have a lot of aluminum in them too, but you can purify them to the point where you can make a ceramic that's almost all silicate. And they're hardened by firing at high temperature. So that changes the structure. That high temperature forms certain types of bonds and networks the solids together. And that's as far as I can go with the description of ceramics. Right? Everybody knows what a ceramic cup is, like a coffee cup, or china or stoneware. Those are ceramics. There are certain cooking utensils that are made out of ceramics that you can just throw in the oven, pull them out, let them cool down a while, stick them on the table and eat straight out. Semiconductors, right? semiconductors are crystalline solids where at least for most consumer electronics, the base structure of semiconductors is made out of pure silicon. So you have silicon atoms in that lattice structure, and you get the tailoring of their electrical conductivities and their electronic behavior by adding other elements. Okay. If you look at the periodic table, let me see. I don't have a readily available copy, just the one on the wall. If you look at silicon, in the periodic table, it has so many valence electrons. Okay. If you substitute, they actually make a type of alloy. If you substitute elements to the right of silicon, they have more electrons in them. So to the right of silicon is phosphorus, and then arsenic down here. So they have one more electron each. When you do that, you form an N-type semiconductor, right? That surface in which they're substituted, or doped, they say, is rich in electrons because of this doping. And if you get electron movement, it's because you have those extra electrons. If you substitute something from the left of silicon, like aluminum or gallium, or even boron, then compared to silicon, you're deficient in electrons. And you produce a P-type semiconductor. P for positive, N for negative. And the way they think of it, although it's not really what happens, they think of it as if the holes are moving. So you have extra electrons on this side, and you have holes on that side. And they judge the movement of this in the semiconductor in terms of N-type, P-type. Okay, and this is sort of a description in molecular orbital terms. With an N-type, you have these extra electrons that are close to the conduction band, or the lowest unoccupied molecular orbital. And then here, you have a deficiency for the conduction band. There are holes down here. So actually, you don't get holes moving, you get electrons moving. And when an electron moves from one place to the other, it leaves a hole behind, right? So if an electron moves this way, the hole moves that way. Okay. So here's an illustration. This arsenic has an N-type semiconductor, is an extra electron. This one is a P-type boron with its hole. Okay, molecular solids. We're going to have to move on. Ionic solids. Here we go. Ionic solids. They can be characterized by having very, very high melting points. It takes 1,000, 1,500 degrees centigrade, maybe 2,000, to melt sodium chloride. Which means they're very stable. The strong electrostatic charges hold them together in their crystal lattice. Now, these crystals, these ionic solids, are non-conducting. They don't conduct heat, they don't conduct electricity very well. They're insulators because everything's locked in place, they can't move. But if you melt them or dissolve them in water, then you free up those ions. They're no longer in the crystal structure, and they can move. Then they become conductors. So there's some nuclear power plant models that use as a heat transfer fluid, liquid sodium chloride. They melt it. And as it turns out, it has extremely high heat capacity. So it's an efficient conductor of heat. What's responsible for the difference in melting points? Well, there are two things. that determine the strength of the intermolecular bonds, or the interionic bonds between the cations and anions of an ionic solid. One is how far apart is the ion. So if the ions are very small, right, there's very short distance between the two, then Coulomb's law says the strength, the force of attraction is very high. By the same token, if the size of the charge is bigger, then you increase the force of attraction. So if you get both of those, both increased charge and shorter distance, you have a very, very strong ionic bond, and that increases the melting point. Okay. Now we're going to go back to the packing model for a little bit. And we look at the types of holes, right, that are in the packing models. One type of hole is the trigonal hole, because it's formed by a triangular arrangement of these three atoms. These types of crystals are too small for a cation to fit in here. So when that happens, these are not very well suited for ionic solids. The tetrahedral hole is formed when there's a sphere that sits in this triangular arrangement. Right? So when you can do that, then you get a tetrahedral hole. Right? And you just draw the centers together in a regular tetrahedron, and that gives it its name. A good example for this one is zinc sulfide. Right? So the zinc 2 plus and the sulfur 2 minus fit together like this. This could be sulfur. The octagonal hole. This hexagonal closest packing gives us an octagonal arrangement. Now, when they lay down like this with each other, then they produce this gap in this octahedral hole. And it's defined by 3 spheres each on each layer. Now, the size of the hole can be quantitatively measured, but we'll be on this right now. But the qualitative arrangement is the trigonal hole is the smallest. The tetrahedral hole is the next largest, and the octahedral hole is the next largest. Now, the size change here dictates whether or not you can fit an occupant in those holes of a given size. Right? So if you need, say in the ionic solids, if you need a large ion to fit in that hole, you want to go for an octahedral hole to fit it in there. But for a smaller one, you might get by with a trigonal hole. Okay, this is a little hard to see, actually. You probably have a table in your textbook similar to this, arranging the atomic solids in network, metallic, or noble gas, and molecular solids versus ionic solids. And it gives you typical types of bonds and properties, and then some examples too. Okay. Now we're going to look at let's see. I was about to say something. I want to check myself. Yeah. Physical properties that are determined by these intermolecular forces. We can look at vapor pressure as evidence for the intermolecular forces. And how does the vapor pressure change with the strength of the intermolecular forces. So if we define what vapor pressure is in terms of a liquid, and you can't see the layer, the liquid is right about here. So what we're seeing is initially you have a liquid in your flask and you stopper it. And it doesn't have to be a vacuum, it doesn't matter. Initially, some of the molecules at the surface of the liquid escape into the vapor phase. They will have sufficient energy. Those molecules, remember, the temperature of this liquid is the average kinetic energy of the molecules in the liquid. And I say average because some of them are high, some of them are low, some in the middle. The high energy ones, once they reach the surface, can escape and fill this space. Initially, it's all one way. But eventually, you get enough of these here in this space that some of them start to return to the liquid phase. So you get an equilibrium setup. And that's what this shows. Now you've got enough of them up here, so you have an equilibrium established. And it develops and exhibits a pressure, a head pressure in this space above the liquid. We call that the vapor pressure. So the vapor pressure is dependent on two things: temperature and the nature of the material. Okay, how strong are the intermolecular forces? If the forces are very weak, then a lot of these molecules have sufficient energy to escape into the pressure, into the space, and that will increase the pressure. Right? So if the intermolecular force starts to drop from one substance to another, then the vapor pressure goes up. So they're inversely related. And this just shows you over time. We call this evaporation into the vapor phase and condensation into the liquid phase. So initially, the rate of condensation is 0 because there's nothing in the vapor phase to return. But eventually, you get enough evaporation to where you get a balance between the evaporation and condensation. Now, this looks like there's nothing happening. You might see the level of liquid drop to a point and then stop. Once you've established an equilibrium and the vapor pressure is constant, then it looks like nothing's happening. But at the molecular level, the activity is furious. Yeah, evaporation and condensation going on all the time. So what's the vapor pressure of water at 100 degrees Celsius? It's kind of a trick question. It's 1 atmosphere. That's the boiling point of water. So its vapor pressure is going to be equal to 1 atmosphere. Okay, here's another way of expressing the vapor pressure in terms of this is at sea level. This is 760 millimeters of mercury, right? Because there's a vacuum up here. But if you actually put some liquid in here somehow, with the rest of it in vacuum, then it'll evaporate and produce a vapor pressure that will reduce the level of that by 24 millimeters of mercury. So the vapor pressure of water it doesn't give the temperature. I assume it's 25 degrees C, which is standard. But if you put ethanol in there, which has a weaker intermolecular force than water, you get a higher vapor pressure, 65 torr. And if you put diethyl ether in there, you get a huge vapor pressure, 545 torr. Okay. This is just restating what I said. Large intermolecular forces translate into very low vapor pressure, which is the case for water. And the vapor pressure will change with temperature, right? Because if you increase the temperature, then you're adding energy to the liquid, and that energy is able to break some bonds. Those intermolecular forces can be overcome by an increase in temperature. So as you increase the temperature here on this scale, you will increase the vapor pressure. And for water, you increase the vapor pressure until 100 degrees is boiling point. But the same thing for ethanol says the boiling point is 78.4 degrees on 1 atmosphere. This is the point at which the vapor pressure of the liquid is equal to the external pressure. And for diethyl ether, it only boils at 34.6 degrees. So if you poured some ether in your hand, which I wouldn't advise, but for argument's sake, it would boil in your hand because normal body temperature is 37 degrees Celsius, and the boiling point of ether is 34.6 degrees. So it would boil right out of your hand. Okay. Let's see, what have we here? Oh, okay. We're developing a formula for relating the vapor pressure to the enthalpy of vaporization. That is, how much heat per mole does it take to vaporize the substance? And this was developed by Clausius and I think it was Clausius first, and then Clapeyron did some manipulations and gave us the hyphenated useful formula. So this is just a derivation, and E, of course, is that natural log base. So if we follow this development along, and you don't have to do this, this is just illustrations, we end up with this arrangement in which the natural log of the vapor pressure is equal to minus the heat of vaporization, right? So the heat of vaporization should be a positive value. You have to put heat into the system. Divided by R, and since this is in units of joules, that would be your 8.145, I think, constant with the joules in it. And then 1 divided by temperature, and of course, this temperature has to be in Kelvin, plus some constant. Now that's one way to express the equation. If you don't know the constant, then you're stuck. So what we've done is we make measurements at 2 different temperatures. And if we do at 2 different temperatures, then we can derive an equation that allows us to do away with that constant that we don't know anyway. And now we have 2 different vapor pressures at 2 different temperatures. And then we can use that information to calculate the heat of vaporization, because the heat of vaporization won't change. It's intrinsic to the intermolecular forces holding those molecules together. Okay, and this is the final version. There it is, 3145, R value. Temperature in Kelvin, enthalpy of vaporization, and vapor pressure. This is the Clausius-Clapeyron equation. And I'm sure that it is in useful information, so you don't have to memorize it. Just know how to use it. Okay, here's an example. Right, we have 2 different temperatures, 25 and 65. And vapor pressure at 25 is this. Heat of vaporization is given. So they're asking, what's the vapor pressure if we increase the temperature to 65 degrees? So in this case, the unknown is the vapor pressure at the higher temperature. And if you solve that equation, come on, there it is. The new vapor pressure should be 194 torr versus 23.8 torr. So it increases quite a bit with that increase in temperature. And notice that you can use any units of measure here. Why? Because they're ratioed and they cancel. So it doesn't matter. You can use torr, you can use pounds per square inch, whatever. The only thing that you definitely have to have is temperature in Kelvin. Okay, change of state. All right, this video is not going to show, so I'm going to pass it up. So what happens? This is one way to express the heating curve of water as it goes through phase changes. We start off with ice, say very cold ice, minus 20 degrees Celsius. And then as we heat it up, it gradually increases in temperature at a constant rate. This is like a time scale. And then once it gets to the liquid, it sits there. Once the ice gets to that temperature, it just stays there as it changes phase. And then once it's all in water phase, in liquid, then it starts heating up again. And then when it gets to 100 degrees, it produces steam. And at that point, the phase change holds it at constant temperature until it's all gas, and then it heats up again. Now, what's happening? Well, in this part of the curve where you have the slopes, the energy that's being put into the system is used exclusively to break bonds. To vibrate, to add energy, kinetic energy to the molecules as they move. When you get to this point, you're breaking intermolecular bonds that hold it in this phase. So you're not adding, the energy that you're adding is not increasing the temperature. It's being all used to break those bonds and convert this, in this case, from liquid to gas, or in this case, from solid to liquid. That's the interpretation as you add energy. So, which would you predict should be larger for a given substance? The amount of heat of vaporization or the amount of heat of fusion? Okay, that's what we call the amount of heat required to melt a solid to a liquid, the heat of fusion. Heat of vaporization converts from liquid to gas. So which one should be larger? Heat of vaporization should be larger. Oops. It didn't say why. Okay, why? Because as you're going from liquid, solid to liquid, all you're doing is breaking weaker forces that are holding the structure in solid phase, and now there's still significant intermolecular forces, but the molecules are able to slide past one another. You're not actually completely breaking those intermolecular forces. Whereas with a vaporization, with a gas, you are adding enough energy to break those molecules apart completely. Now they're independent agents. That takes a lot more energy. Okay, what's a phase diagram? Well, phase diagrams can become extremely complex. So we're going to use the very simplest type here to describe what a phase diagram is. A phase diagram relates the, well, let me show you. It's easier to explain that way. If you have temperature on this scale, low temperature to high temperature, like this, from left to right. And for this one, it's in particular, it's for carbon dioxide. So carbon dioxide is, you see 3 regions of this phase diagram, and they're separated by lines. So this region is all gas. This region is liquid. This region is solid. There's your temperature scale. There's your pressure scale. So what this is saying is that at any one of these lines, you are at a boundary point where you have both phases together at the same time. If you have pressure and temperature right there. So this temperature and that pressure gives you both phases simultaneously on that line. And in this case, this is solid to gas, this is solid liquid, and this is liquid gas, the way they're related. So at this high pressure and this high temperature, you can have liquid and gas together, right here, along that line, anywhere, with that combination of pressure and temperature. Okay. So these are the various phases. And if they're not identified, the solid is always here, the liquid here, and the gas here. Because this gas is at low pressure, high temperature. That's a clue that it's going to be a gas. But even at high temperature, if the pressure is high enough, you're still going to have a liquid. But if you increase the pressure and decrease the temperature, you're going to get a solid. Okay, these are phase lines. There's one point on this graph and on many graphs of a phase diagram where you can have all three phases together at the same time. That's known as the triplet point. So at this pressure and this temperature, you can have solid, liquid, and gas all together at the same time. Notice also the difference between the solid and the liquid. Usually, the slope on this line between solid and liquid is a positive slope. It slopes to the right. Okay? So, if we were to say, all right, I have a solid that's at this temperature, and I'm going to keep it at that temperature. But what I'm going to do is decrease the pressure. So as you decrease the pressure, it goes through a liquid phase and then into a gas phase. But if we have a lower temperature, we go and follow at that temperature, decrease the pressure. It's going to go through the solid phase, straight into the gas phase. It sublimates. Or if we hold the pressure constant and change the temperature. So let's say we have, we're over here in the gas phase, at this high temperature, at this pressure, and we hold the pressure constant and cool it. It goes from gas to liquid, and then liquid to solid. Okay. Notice the phase diagram for water. Right? Solid, liquid, gas. The main difference is the slope of this line. For water, the slope of the line is negative. So rather than the previous one, where as you increase the pressure, you go from gas to liquid to solid, or gas to solid, with water, you go from gas to solid to liquid. Some substances do that. Okay. For each one of these, let's see, we've defined boiling point, viscosity, surface tension, enthalpy, freezing point, vapor pressure, heat of vaporization. Okay, so we've defined all of these. What I want to do is, as you increase the intermolecular force, what happens to each of the following? For boiling point, if you increase the force between the liquid molecules, you increase the boiling point. Right? How about viscosity? If you increase the force, you increase the viscosity. It makes it more difficult to pass through that opening. Surface tension. If you increase the intermolecular forces, you increase the surface tension of the liquid. You increase the intermolecular forces, by definition, you increase the heat of fusion. How about the freezing point? You increase those forces, then it takes more energy to break them, and the freezing point also increases. If you increase those forces, you hold molecules in the liquid more effectively, and you decrease the pressure in the headspace. So this one is opposite. You decrease the vapor pressure with increasing intermolecular force. And the heat of vaporization, that's the heat required to go from liquid to gas, you also increase that one. So as you increase the intermolecular forces, each one of these increases except for vapor pressure.